All right. I'll read the question, start thinking about it, and start planning as to what's going on. A baseball, mass of 140 grams, traveling 32 meters per second, moves a fielder's glove backward. I'll read again. A baseball of mass 140 grams, traveling at 32 meters per second, moves the fielder's glove 25 centimeters when the ball is caught. Do you get the picture of the whole thing? Yeah. So the ball is moving, fielder's glove is here, catches it, the fielder's glove moves backward, and it says it moves back 25 centimeters. I'll read over again. A baseball mass of 140 grams, traveling 32 meters per second, moves a fielder's glove backward 25 centimeters when the ball is caught. What was the average force exerted by the ball on the glove? Force exerted by the ball on the glove. So here is a ball, 140 grams, moving at 32 meters per second, and that's a fielder's glove. The fielder's glove is pushing the ball which way? Should be pushing this way, right? But as the fielder's glove intercepts the ball, the fielder's glove moves backward a distance of 25 centimeters. The question that is asked is, what force is the ball offering on the glove? Okay. What is the force offered by the ball on the glove? Now, the object that is actually in motion is the ball. So let's find the force on the ball. Okay? So how do you work this out? What is the line of thought? How do you think about this problem? Like, how do you start? What kind of energy does this ball have? What happens to the kinetic energy?
It changes.
Like after it's caught, what is the kinetic energy? 0, which means the kinetic energy is gone. Somebody stole it. Like what took it off? Somebody did work against the ball, right? Somebody did a negative work on the ball. That's why the kinetic energy dropped to 0. So basically, the idea of this problem is this. The change in the kinetic energy that the ball is undergoing is equal to the work done on the ball. Whatever change the ball is experiencing is all because work was done on the ball, correct? Okay, what's the change of kinetic energy? What's the final kinetic energy? 0. What's the initial kinetic energy? Half. What's the mass? 0.140 times 32 square. So this is the change in kinetic energy. You understand why I put 0 first here? Why? Because that's the final kinetic energy. This is the initial kinetic energy. So the change in kinetic energy is final minus initial. Make sense? Is equal to work done. What's the formula of work done on the ball? Force times? How much is it? 0.25. Can you figure that out? This will be the force on the ball. Find that out. This will be the force on the ball by the glove. Work it out. Calculate it. So the glove is pushing the ball in this direction. This is a force on the ball that you're trying to find out. How much you get? Negative?
286.7.
So basically 287.
Yep. Yeah.
Is that everybody's answer?
Yeah.
Good. That's a force on the ball. But the question is asking, what's the force on the glove by the ball? What is it?
It's the same.
Same, but
Not negative.
the force on the glove is 287 newtons positive. Newton's third law pair. Both are actually supposed to be equal. So you can see the CFB is negative 287. Can you see which way the ball is being pushed? This way. So, but the ball is pushing the glove in that direction. That's why the glove moves back. So try to understand the physics behind it. It's not difficult to grab it. Any questions on this? Okay. Change in kinetic energy is the work, and the work done on the ball is our concern. The change in kinetic energy of the ball is the work done on the ball. And so we did this. So automatically you get a negative answer indicating the force is this way, not that way, which is on the ball, but on the glove it's supposed to be the other way around. Okay? No questions? Does it mean that everything is clear or nothing is understood? Chris, you the final verdict. Good.
I'm clear.
You're clear. Nick? Good. All right. Next one. If the speed of a car is increased by 50%, the speed of the car is increased by 50%, by what factor will its minimum braking distance be increased? Assuming everything else is the same. In other words, the driver's reaction timing and all those things are exactly the same. So, you understood the problem? If you increase your speed by 50% of your previous speed, and if you slam the brakes, what will be by what factor will the braking distance be increased or changed? Braking distance, you know what is braking distance? So imagine you're going at some speed, you slam the brakes, and the car grinds to a halt. That's the braking distance, minimum, right? Yeah.
It could be 2.25.
You're right. You are perfectly right. How did you do it?
Well, velocity is square, and so I just took two numbers, 100 and 150.
You
Squared
did
them
by
together.
trial and I mean like by numbers. You really did by numbers, right?
Yeah.
Okay. So what did you find by that?
And I divided the answers I got by each other.
Okay. But why? How is the distance connected to it?
Well, I just know that velocity is square in the equation.
Velocity is squared, yes. But why is well, the question is about the distance, not about the velocity. Yeah.
The kinetic energy formula is equal to half mv squared. And if we assume everything except v stays the same, and it's 1.5 times the original, if the velocity just say 1, and then we have 1.5. So say the initial velocity is x, and the final velocity is 1.5x. If we square that, it'll be in the original x will equal just x, or x squared, and then final velocity would be 2.25 x squared, and then
Okay.
work is equal to fd.
Okay. There comes the d factor. Work is equal to fd. So what you should be doing here is again the same thing. You are going to take away all the kinetic energy of the car by doing work, right? So half mv squared is equal to fd. Let's call it d1. The first time you're slamming your brakes, you stop at distance d1. Now if you make the speed 50% more, which is 1.5 v, and when you square it, what do you get? 1.5 d square, and that will be f d2, because now this braking distance is changed. Braking force is the same, but braking distance is changed. Open this bracket, you'll get half m 2.25 v square is equal to f d2. Now divide this equation with this equation. Divide the first equation with the second equation. When you divide this with this, what do you end up getting? Half mv square over half m 2.25 v square, and you'll get f d1 over f d2. What do you do now? Cut, 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 cut. What is left? What is on this side? On the top is 1 over 2.25 is equal to d1 over d2. So what is d2? Cross multiply. It will be 2.25 d1. So your new braking distance is 2.25 times the old braking distance. You see, you don't have to use numbers. You just use variables and get there. The question is, how much is the percent increase in the braking distance? How much? The question was, what is the percentage increase in the braking distance? %125%. That's right. 125%. D1 is like 100. That's like 100%. But D2 is going to be 225. So how many times or what percentage is changed? So you know how to find the percentage change, right? How do you find percentage change? Percentage change is change over original times, that is percentage change. What's the change? Earlier it was D1, now it is 2.25 D1. What's the change? Change is 2.25 D1 minus D1. That's a change, right? Over original, which is D1 times 100. So it will be 1.25 times 100. So 125%. So the new distance is 125% more than the old distance. Yeah.
Why is it 1.25?
Because 2.25, when you take D1 common, if you take D1 common, you get that. And then the D1 is cancelled. So you have 1.25. Okay. Questions? No? All right. Jane, looking for Tarzan, is running at top speed, 5.3 meters per second, and grabs a vine hanging vertically from a tall tree in the jungle. How high can she swing upward? Does the length of the vine affect your answer? So, you understand the story? Okay. I don't ask me why is she running and all that, but she's running. That is Jane. She's running at top speed of 5.3 meters per second. She's running and then she's trying to hang on to this vine. So she grabs the vine, and what happens after that is that the vine will start swinging. So the vine swings to a certain height, and then it'll swing back. But normally their goal is, as soon as it goes to the maximum, you let go of that and hold on to another vine, and then kind of swing down again, and that's how they kind of swing from tree to tree. All right, so what are you going to do? How you will find out the height? The question is only asking for this height. The question is asking for how high can she swing upward? How high can she go up? Yeah, what is the starting point? Yeah.
Would it be that kinetic energy?
Converted to?
It would be converted to GPE.
That's it. So Jane will have a kinetic energy over here, and with reference to that level there won't be GPE, but when she goes there she gets GPE while she just stops. That means no kinetic energy, and then she'll come back. So all you do is just equate the two. So the kinetic energy that she's going to lose is the GPE she's going to gain. So half m 5.3 square is equal to mgh. Mass cancels. So find out h. 9.8 is gravity. What's the answer?
1.43 meters.
Yep, 1.43 meters. So she swings to that height and then stops and comes back. So the concepts are straightforward. All you have to do is apply. And the second part of the question says, does the length of the vine affect your answer? Yes? No? No. That's true. Even if the vine is a mile long, she's still supposed to gain that much GPE, which means the elevation is exactly the same, right? The elevation part of it is exactly the same. But that's, of course, ignoring air resistance and stuff like that. So if the vine is very long, it's possible to gain that height. She will have to swing a long distance, right? And then there will be more air resistance and more loss, which means she won't go to that height. But if the vine was short, it's easy to kind of get there. You see it? Yeah. So, well, if there's no air resistance, then 1.43 meters is the max it can go. Next one. A 65 kilogram trampoline artist. A 65 kilogram trampoline artist jumps vertically upward from the top of a platform with a speed of 5 meters per second. How fast is he going to land on the trampoline 3 meters below? So that's a trampoline. Okay. Now, obviously they're saying there's a board. This person is jumping straight up at 5 meters per second. And what happens when you jump straight up? Goes like that. The question is asking how fast will that person land on the trampoline. Now you can do some of these questions with equations of motion. Correct, Chris?
Can I stand again? Is that okay?
Yeah.
Thank you.
Welcome to do anything other than that. Or if bright light will keep you awake, then turn this on. Alright, so the question is this. Jumping up, oh, this is 3 meters. That's also given. I'll read again. A trampoline, 65 kilograms. So 65 kilogram trampoline artist jumps vertically upward at 5 meters per second. How fast is he going to land on the trampoline? 3 meters below. Do that first part. So what can be done? Of course, you can use equations of motion and do it, but you don't want to do it that way. You want to try and make things using the energy method, which is much easier. You already saw it. Energy method is far, far easier for many questions. So what is your line of thinking here? You have an answer? No? Brandon?
Well, I know that he gains, or he has kinetic energy going up,
He has kinetic energy here. Okay. What happens?
and then I guess he gains gravitational potential energy,
And he goes there. Okay.
and
Then he loses it.
goes back to kinetic energy going down.
Goes back again to kinetic energy. Then
Until he hits the bottom.
it's the bottom. So how do you start? Where do you start? Energy conservation. What do you mean by energy conservation? The energy at two different spots should stay the same. So whatever energy he has got at this point should be equal to the energy at this point. Yes.
Doesn't he lose the gravitational potential energy at the 3 meters?
From here to here?
Yeah.
Yes. Yeah.
So, isn't that equal to kinetic energy?
But he has kinetic energy already.
Kinetic energy plus gravitational potential energy.
So this is the thing. If you're considering this level to be zero potential energy, if you consider that to be zero potential energy, then what energy does he have at that spot? What kind of energies does he have? He has got gravitational potential energy and now, considering this to be the zero level of gravitational potential, what energy does he have here? Only kinetic. Then equate the two. That's all. It's just an accounting sort of thing. So the GPE at the top plus the kinetic energy at the top should be equal to the kinetic energy at the bottom. So this is kinetic energy 2, and that's kinetic energy 1. So all you're doing is just substituting mass m g times 3 meters height plus half m 5 squared equals to half m v squared. That's what they want you to find out. What can you do from that equation? Cancel out the mass, divide the entire equation with mass, mass is gone. So we have 9.8 times 3 plus 25 over 2 equals to v squared over 2. What is v? Find out. 9.2 meters per second. That's right. So the velocity with which he's going to land, the speed with which he's going to hit the trampoline is 9.2 meters per second. That's the first part of the question. The second part of the question says, if the trampoline behaves like a spring with a spring constant of 62,000 Newton per meter, how far does he depress it? Okay, so the question is now a different question. It's a totally different question. It says, all right, now you know that he's landing here. What happens after he lands? He makes the trampoline sag, right? He's making the trampoline go that far. He's depressing it by that much. They're asking you how much is getting depressed. And they also told you the spring constant is, how much you said? 62,000 Newton per meter. That's the spring constant of that trampoline. Now let me know what ideas come to your mind. What kind of energies are we talking about? Yeah.
Would you connect the kinetic energy when it's hitting down there with the elastic potential energy?
Is converted to elastic potential energy? Any other? Is the kinetic energy the only reason why it is getting the elastic potential energy?
Plus GP.
Huh? It's losing height as well. That means it's losing GP as well. So you have to think properly. So, all right. So if you're going to consider this level to be, if you're considering that level to be zero potential, right? So what's the GPE here? What's the KE here? Half m v square, right? You already know the v. So it has a GP of 0 and KE something. When he goes down here, what's the KE here? Nothing. What about GPE? Negative, because he's going downward, right? It's negative mgh. Do you understand that point? Because you're considering this level to be zero level. So if anything goes below, it's going to be minus. If anything is above, it's plus. So that is minus mgh. What else does it have? Elastic PE, elastic potential energy. What's the formula? Half K? What's X here? H. Half kx squared, but the x is h, because that's the depression. So all you're going to do is equate this with this. We're going to equate those two. So let's do it. So GP is 0, I'm not concerned about it. Half m 9.2 squared, right? That's the kinetic energy right there. Nothing else. It has nothing else there. Should be equal to no kinetic energy, but then minus mg times h and half kh squared. This is the real thing. Now you can't cancel m here because why can't you cancel m's? Because there's no m on this side. So we have to use the 65 kilograms. So half 65 9.2 square is equal to minus 65 times 9.8h plus half of 62,000 h squared. What kind of an equation is that? It's quadratic. Well, we have to manage it now. So can you tell me how much is this number here? This whole thing. (9.2 squared divided by 2 times 65.
2,750.
2,000?
750.8.
Okay? Is equal to, what is this?
It's 637.
No, no,
Negative.
only this.
Yeah.
Oh, 637?
Yeah.
Okay. Plus 31,000 h squared. Now what you do is shuffle it up in such a way that it makes it into a quadratic equation. 31,000 h squared minus 637 h minus 2751 equal to 0. Okay? And then use the equation minus b plus or minus b squared. So 637 minus plus or minus square root of b squared minus 4 times a times c, so it's already plus because of this. 431,000 times 2751 over 2a lot of numbers. What you can do now is leave this as the 637 plus or minus. Just tell me how much is this. Do only that part. Do this first. Do 4 times 31,000 times 2751 and then add 637 squared to it. Whatever answer you get, take the square root of that answer. What do you get?
18,480.5.
Okay? Divided by 62,000. Now, of course, minus is not going to be an option, so take plus. So take plus and work. How much is it?
0.3 meters.
0.3? 0.31 meters, that much. That's pretty realistic, right? Trampoline going down by that much. That's realistic. So 0.31 meters, that's what you should get. Now sometimes some books, they ignore that GP part of it. They ignore it because it's not too big. The major things are the kinetic energy and the other one, but you can't totally ignore it. Because even if you don't use the kinetic energy, if you just land with 0 speed on the trampoline, you still will go down, right? So it is definitely there. But in case you ignore that part of it, this part of it, then the expression is only this. This is equal to this straight away. Check it out and see what you get. If you're going to equate that way, what will you end up getting? Half 65, 9.2 squared, that's the kinetic energy while landing, is equal to half k h squared. So half 62,000 h squared. If you do this, the half cancels off and you can see what h is. It will be wrong, but close. How much?
0.29, that's
0.3, approximately 0.29 something, so 0.3. You can see that there is it is close enough, but it's not correct. Okay? So we have to account for all sorts of energy while it is moving from there to there. Any questions? I'm showing you all the different varieties of problems. And no matter how many different type of problems you do, still you'll find every problem is a new one, right? That's how you learn physics. That's why physics is considered kind of hard by some, because you need to know how to put all the information together and think in a fresh manner. That's what is, it's not like biology, where you learn something, you memorize something, you learn the new words, and you learn the mechanism of what is happening, and then just spit it out. So basically, you're going to be asked about, what is the function of this? Your answer is ready. You won't have the answer unless you study it. You can't just generate your answer. So you need to really sit before the exam and really do a lot of memorization, like, repeating what you said again and again, so that the process is just put down without any mistake, purely out of recollection. But physics is not like that. If you understand all the concepts, then you have to put it all together in a totally fresh manner, not from past experience. You get it? You cannot use a past experience to work something out. It's a new problem. Read it. All right, this is a situation. What's going on? And then, so that's the reason why we are doing all these things, so that you are not programmed to do only one task, right? You're not just programmed to do one thing, because if you're programmed to do only one thing, if some strange kind of wording comes up or strange situation comes up, then you'll be totally lost. You can't apply the physics there. So what we do primarily is to learn physics properly from A to Z, and then now you have the physics knowledge, you can apply it anywhere, right? It's like flying. When you fly, you go from one place to another place. Now, if you continuously fly in the same place again and again, you may be doing it by pressing the same sort of buttons and doing the same things, absolutely. And if you only learned that, what will happen if there is a new situation coming up? One of the engine fails. Okay, those are all new things. Or you're landing in snow, or there is hail, or there is something else going on. So you are faced with new situations. Now, if you're knowledgeable of everything on the aircraft, and knowledgeable about every sort of communication that you could potentially do, then you won't be, frightened about it. Okay, you're faced with this situation, you manage it. Like the pilot who landed in Hudson, he had to do it, he did it, and everyone was safe, right? So, which is the way what he did was perfectly right, because there's no way he could reach the airport, and therefore he had to land it somewhere. That's the problem with the planes. It's not like a car, you just drive, the engine stopped, okay, go to the side, pull over. But plane is not like that. The engine stopped, and that is panic. Okay, one engine stops, still there is panic, because using only one engine is going to have overloading. So you need to kind of find a quick place to stop. If you keep flying with that one, even that one can fail. Overloaded. So imagine both engines are lost because the birds jammed it. And thinking of a big plane such as that, it's not a Cessna where you can land on a field. So you need to land on water. Anyway, so why I'm saying all this is, you're learning physics concept-wise, and then I'm just throwing the option of you can do multiple things with any chapter. So as you keep learning chapters one by one, you become more and more knowledgeable about, yeah, I can use this, hey, I can do this. And now I don't have to use equations of motion, I can use energy conservation. So you just start getting ideas of different processes, and then implement it. That's how it is. And that's why students find it hard, because it is not memorization and repetition. So some of my good students who did pretty well, they told me that they never prepared for physics. They never really prepared for physics because they were paying attention in the class and they were absorbing everything. And luckily they have the retention capacity too. So what happens is, like, physics, no preparation required. They just come blank. And then, okay, what's the question? All right, here's the question. All right, think fresh and answer. That is how physics should be tackled. Sitting and studying physics is actually not the right thing. Okay, I'm pretty sure most of the time that you spend is doing mastering, right? Not learning physics. Okay. Come on. That's a long time. Everything's okay?
Yeah, I'm late.
Just coming from home?
No, I came from Kenway. And
Oh, you're done. Okay.
yeah, we just
Perfect. I was thinking that you're all going to meet tomorrow or something like that.
I was gonna come in for advising, but I thought it was Wednesday. So
Good. At least you're not missing much, but I'm recording too, so you will
I
have
can watch
everything.
that too.
Good. So yeah, I was just talking about the different possibilities that you can actually have in problem solving. Okay, so never stick to one method and say, I know how to do this problem. But then what if you do all these things and suddenly when you look at a question and says a submarine in the water, this, that, and then you'll be, I never did a submarine question, so I'm done. You cannot let go like that. You'll say, all right, what is the matter? Let's find out. Submarine or whatever it is, what is going on? And how can I apply the concepts that I've learned in there? And then you see the mechanics of what is going on and then apply. And once you apply it, you'll say, oh, it was actually an easy question. You know, normally that's what happens. Students actually think every question is tough, hard to crack, and then mess the whole thing up. Instead, just look into what is going on in that question and then you'll be able to answer. Next one. A projectile is fired at an angle upward, at an upward angle of 45 degrees from the top of a 265-meter cliff. A projectile is fired at an upward angle of 45 degrees from the top of a cliff. So here's a cliff. The projectile is fired at 45-degree angle at a speed of 185 meters per second from the top of a 265-meter tall cliff. And the question says, what will be its speed when it strikes the ground below? What will be its speed when it strikes the ground below? When it strikes here, what will be its speed? Yeah. That's all it's given. If the same question was asked long back, what would you have done?
Resolved it.
You would have resolved it and then split it up, put in the table and all those things and found out all the velocities and, finally you'll end up getting there. In fact, we have done problems like that. But now we are looking at it from a different angle. What angle? Conservation of energy. Yeah. So, in terms of conservation of energy, what kind of energy does this have over here compared to here? Over here it has GP and over here it has just kinetic energy. So let's call it kinetic energy 2 and kinetic energy 1. Equate. Just equate it. So mgh plus half mv1 squared should be equal to half mv2 squared. That is your main energy conservation equation. And then if you knock the mass out, we have the equation gh plus v1 squared over 2 is equals to v2 squared over 2. You know everything on the left hand side. Substitute. 9.8 times 265 plus 185 square over 2 is equal to V2 square over 2. Find V2. So it is coming and hitting at 199. And if you want to know the angle, you have to know the horizontal component. The horizontal component will stay the same everywhere. And that horizontal component is 130. So you can get cosine of theta as 130 over 199. And you solve for it. What angle is it? 49 degrees. Next one is a block of mass m slides without friction along a looped track like this. It's not like wheels or rails or clamped like that. It's not like a roller coaster, just a slide. So it's zero friction, so it goes like that and turns around and goes. Okay. Now the question is, a block of mass m slides without friction along the looped track. If the block is to remain on the track even at the top of the circle, if the block is to remain on the track even at the top of the circle, whose radius is r, from what minimum height must it be released? From what minimum height must it be released? Yeah. Can you release it from here? No? What's the problem? Yeah, if you release it from here, it's not going to reach all the way up there. So where should you release it from? From the top. No, I just extended it so that you can actually start from wherever. Minimum. You know, of course, you can go as far as possible and release it. Then, of course, that will happen. But you want the minimum. You can't do it from here, right? So where?
The same height where it's equal.
From here? Why?
Because the GPE is going to be the same.
Because the GPE that is here should be the same, is what he says. Is it okay? Yes? What's the problem with that?
Oh, there's no kinetic energy.
There's no kinetic energy. What will happen then?
It'll
It'll just fall straight down. So if you're going to release it from here, it'll go like this, and before even it could reach there, it'll just drop off. It won't reach there. It goes like this and stop, fall. They want you to make it go in a complete path.
That's be more than
It has been more. That's for sure. But where? We need an exact answer in terms of R. It's not a problem, but it's an algebraic problem. They are asking you what height will you release it from in terms of R. Now for this turn to be completed, is there any requirement? Is there any condition required for this to make a complete turn? Yes? Huh? Centripetal force. Yes. In order to make a complete circle, see, it has to have a speed at the top for it to keep going. See, that one. It has to have a minimum speed on the top. And the minimum speed on the top is when the normal reaction is not there. That's a minimum. So the only force is mg, and that mg is equal to mv squared over r. So the v squared is equal to gr, or v is equal to square root of, haven't you seen that before? The minimum speed required on the top is root of gr, you've seen it when we did some problems. The minimum speed required on the top is square root of gr. So the speed over here with which it is supposed to move is square root of gr. Now, since you know the speed is square root of gr, what can you do now between here and here? What energy does it have with respect to this level? Okay, which is mg. And what energy does it have over here? Kinetic and GP. So at this level it has kinetic energy and GPE. Now you're going to equate the two. So mgh on the top is equal to kinetic energy over here, which is half m v square. Where's v? What is v square? gr. And then potential energy is mg. What's the height? 2r. Now m can go. So we have gh. Oh, g can go. G is gone. So we have h is equal to 0.5 r plus 2r. So what's the height? 2.5 r. That means like this is r, that's 2r, 2.5 r. If you release it from there, it will just barely make it. But if you release it from further up, definitely it will make it. Yeah.
So that would be true for every situation.
If there's no friction. Yeah.
No friction.
If there's no friction, and it does not depend on gravity. Can you see gravity is gone? Which means on the moon, if you do that, it should behave the same way. It should do the same thing because gravity is knocked off. So if you do the same thing on the moon, it should do the same things. From 2.5 r, if you release it, it will make the turn. Next one. Huh? You said something?
Kind of more of a conceptual, like, would you have friction on it?
Friction will be there. That's the reason why. So if friction is really there, if you release it from here, it is not going to be able to make it there. So if friction is already there, you have to compensate by giving some more extra energy. So the friction will do some negative energy, right? Friction will do negative work, right? So if you compensate by providing some extra GPE, then it will make it. It's not easy to find the frictional force, why frictional energy, because from here to here you may be able to evaluate the friction. But from here to here, the normal reaction is continuously changing from a maximum here to 0 there. So it changes. Still, it's doable. You can take an average and all that and still work it out. Yeah.
So problems like that when it's on sliding and you're equating with friction in it, would it be mgh minus the friction, or like minus?
Yeah. Exactly. If some friction is doing some work, you have to take away from mgh. Yeah.
You have to have gravity, but it doesn't depend on it.
Exactly. You have to have gravity for it to move, but it does not depend on gravity. The height part of it does not depend on gravity. Yeah. Any other questions on this? Next one. A ball is attached to a horizontal cord of length L. A ball is attached to a horizontal cord of length L, whose other end is fixed. If the ball is released, what will be its speed at the lowest point of its path? If the ball is released from here, what will be its speed at the lowest point of its path? How fast is it going to move here? That's the first question. How do you do it? So considering this level to be the bottom, what energy is going to convert itself to? mgh is getting converted to? Just equate it. Just equate those two, you should be getting the answer. So how fast is it moving at the bottom? Just equate those two and you'll get the answer. So how much is mgh? mgl is equal to half mv squared. So cancel the masses, they get v as square root of 2gl. That's the first part of the question. The second part of the question goes like this. A peg is located at distance h directly below the point of attachment of the cord. This is the point of attachment of the cord. They're putting a peg here. A peg means like a nail. So what will happen if a nail is fixed over here? What will happen? Look at this. Oh, perfect length. What will happen is it will fall this way, and when it comes here, the nail will stop it here, right? So what will happen is this part will start curving up and making a circle. Like this. See? You see that? I can show it over here. If I release it, now if I release it from here, it won't make a turn. See, it didn't make a turn. But if I put it at the right place, it could complete the circle. Alright? So they're telling you that at some point, at a height h, from this point, there's a peg attached. So now it's going to rotate like this. Now if h is 0.8 L, if h is 0.8 L, what will be the speed of the ball when it reaches the top of the circular path? What will be the speed when it comes here? V equals to what? When it reaches this part. It's moving with some speed. What speed will it have there is the question. So work the same way. Work exactly the same way. What energy is it losing from there? mg? So the energy here is mgl, correct? What energy does it have here? GPH, mgh. Well, how much is h?
0.2 or 0.4.
0.4 L. Look, they said 0.8 is from here to here. So what is this? If that is 0.2 L, what is the height? 0.4 L. Do you understand that part? Because they said from here to here is 0.8 L, the rest of it is 0.2 L, correct? And if this is 0.2 L, that's radius. One more radius on the top is another 0.2 L, so 0.4 L. And what else does it have over here? Kinetic. Plus half mv squared. We want to find out v. So what do? Equate the two. So if you equate the two, you have mgl is equal to 0.4 mgl plus half mv squared. So if you knock off all the masses and multiply the whole equation with 2, so you get 2gl is equal to 0.8 gl plus v squared. Then you subtract. What is 2 minus 0.8? 1.2 gl is v squared. So what is v? Square root of? Oh, 1 point. square root of 1.2 GL. That should be the speed when it comes over here. Alright, so seeing different varieties, and we will start off with chapter 7 in the next class.